In this video, we are going to start with the representation of a band-limited signal and then consider the case when the frequency of the highest frequency component of the band-limited signal tends to infinity. In other words, the signal becomes a signal which is not band limited. So in that case, what type of a representation shall we obtain? That is the question to be answered. So let x of t be a band limited signal. That is the Fourier transform of x of t. In fact, x of omega is equal to 0 for magnitude omega greater than a given omega m. So for omega greater than omega m or omega less than minus omega m, x of omega is equal to 0. So we have a band-limited signal. So omega m is the frequency corresponding to the highest frequency component of the signal. Okay. Now, we have seen that if x of t is fed as the input signal of an ideal low-pass filter with cutoff frequency omega c greater than omega m, all of the signal will be passed through the system, through the ideal low-pass filter. So the output will also be x of t. So let x of t be the input signal of an ideal low-pass filter with cutoff frequency omega c. In fact, the frequency response of the ideal low-pass filter is the frequency response of the ideal low-pass filter is given by the following expression: capital H LPF of omega is equal to 1 for magnitude omega or absolute value of omega less than omega c and 0 otherwise. Okay, and remember we have calculated the impulse response H LPF of t. The impulse response of the ideal low-pass filter has been calculated as by using the inverse Fourier transform of the frequency response, capital H LPF of omega, as sine omega c t divided by pi t. So if we have the ideal low pass filter here as a system, ideal low pass filter as a linear time invariant system with this impulse response, if the input is x of t, the output will also be x of t, because the cutoff frequency is greater than omega m. Omega c is greater than omega m. So this is valid provided that omega c is greater than omega m. So all frequency components of the band-limited signal will pass through this system, the ideal low-pass filter. Okay, and we know that x of t, the output, is the convolution of the input, which is again x of t, with the impulse response. And therefore x of t is from minus infinity to plus infinity, x of tau h of small h, the impulse response, evaluated at t minus tau and integrated with respect to tau, or it is sine omega c t minus tau, okay, divided by pi t minus tau integrated with respect to tau. Okay, and we know that this is the representation of a band-limited signal in terms of the input-output relationship in an ideal low-pass filter with cutoff frequency omega c greater than omega m, the highest frequency component of the band-limited signal. Now suppose that we consider band-limited signals with gradually increasing omega m. Omega m increases, and in the limit it tends to infinity. So suppose that we consider band-limited signals with gradually increasing omega m. Since omega m increases, we have to choose an ideal low-pass filter with, again, omega c increasing with omega m. So in this case, we have to increase the cutoff frequency of the ideal low-pass filter omega c such that omega c is greater than omega m. So omega m is increasing and correspondingly omega c is increasing. And in the limit, as omega m tends to 0, omega c will tend to, as omega m tends to infinity, omega c will also tend to infinity. So as omega m tends to infinity, that is, the signal is no longer band limited. Omega c will also tend to infinity. Okay, as omega c tends to infinity, therefore h LPF of omega will tend to 1 when omega c tends to infinity. Okay, that means it will be a system which passes all frequency components. Because we have the band-limited signals with gradually increasing omega m, and correspondingly the cutoff frequency of the ideal low-pass filters we have to use for such signals will have a cutoff frequency also gradually increasing. And in the limit, as omega m tends to infinity, omega c will also tend to infinity, and therefore the frequency response will tend to 1. And therefore the impulse response will be equal to the impulse. Okay. Now we can also see this from the impulse response, sine omega ct divided by pi t, when omega c tends to infinity, will be, now sine omega ct for t close to 0 is approximately equal to omega ct divided by pi t. So at 0, the value is omega c divided by pi. So when omega c tends to infinity, the value at 0 will tend to infinity, and the 0 crossings will be very close to 0. Okay, they will get closer to each other and they will become very close to 0, and therefore that sinc function, the impulse response of the ideal low-pass filter, will tend to an impulse. Okay, and the representation, the signal representation for this limiting case will be x of t equal to, from minus infinity to plus infinity, x of tau delta of t minus tau integrated with respect to tau. So we obtain this well-known expression. That means the representation of an arbitrary signal in terms of a superposition of shifted impulses, which has a very important role in signal theory, is the limiting case of the bandpass signal representations. And how did we obtain this result? We have assumed that the frequency omega m in the representation or Fourier transform of the band-limited signal gradually increases, and in the limit it tends to infinity. In this case, the cutoff frequency of the ideal low-pass filter will also tend to infinity, and the frequency response will be equal to the constant 1 for all omega, from minus infinity to plus infinity, which is nothing but the Fourier transform of the impulse. So the impulse response becomes the impulse in that case, and we are able to observe this from the behavior of sine omega ct divided by pi t when omega c tends to infinity, and we obtain the representation, the signal representation for an arbitrary signal in terms of a superposition of shifted impulses. Okay, thanks for watching.